Hello, and welcome back again to this introductory unit to design with the Verilog language. For the rest of this unit, we're going to cover these three topics. That is, the general structure of the Verilog module, just so that you have a general idea of what this looks like, a brief discussion of Verilog versus VHDL, and finally, since we've already described how to describe flip-flops in synthesizable Verilog, let's turn to how to describe combinational logic. This is the overall typified structure for a Verilog module using an example of a flip-flop. Of course, a flip-flop is too trivial to put into its own module, but it does create a simple example that we can already understand based on what we've seen so far. Now just look at the features within this module. At the top we have the module name, and of course you can use any name that's not a reserved keyword. We then have a list of the connected ports, followed by the port declarations. Port declarations indicate the direction of the port. This is hardware, so wires, except for certain shared buses, go in one direction only, so the inputs or outputs. And in addition, though you can't see it here, you will also specify the width of the port in the number of bits. In this example, they're all 1 bit wide. We then declare our local variables. We actually don't have to declare variables that are also outputs, but I think it's a good practice to make sure you're consistent in your variable declarations. We then have our code segments. Here we have only one code segment, a procedural block describing a flip-flop, but in practice we'll have multiple code segments. And one distinction in RTL is these code segments are all independent of each other because they are modeling the intrinsic parallelism of hardware. And that's a big difference to the serial code within a procedure in a language such as C, which obviously only executes serially. Here we can actually capture the implicit parallelism. We'll come back to that more later. And finally have the end module without a semicolon that indicates that the description of this module has ended. We'll see more examples of this as we enrich our knowledge of the Verilog language in later units and modules. In contrast, this is the VHDL model for a flip-flop. I'm not going to go through the details here, but you can see there's an overall description, including the ports, and then a description of the behavior inside the flip-flop. One thing you might notice, however, it's a lot more typing than in Verilog. There's more complex structures within the VHDL language, and thus more text to enter in order to describe anything. A little bit about Verilog versus VHDL. Verilog, which is based on C, that might already be apparent to you, was originally a Cadence proprietary language, but for a long time now it's been an IEEE standard that can be freely licensed. It's quick to learn because it is based on C, and frankly it's also easier to read and design than VHDL for much the same reasons. It tends to be very popular in the United States. Most design companies in the United States use Verilog. And because it's a simpler language and a more popular language, it tends to have more tools supporting it than is the case with VHDL. VHDL, on the other hand, arose from a Department of Defense program, and it's based on a strongly typed language called Ada, which is now defunct. It is also an IEEE standard, and in fact became one before Verilog. It is much more structured than Verilog. It doesn't give us many alternative ways of doing things, which can be good. It actually has more features than Verilog as well, though Verilog made up for this a lot when the system Verilog standard came out in 2005. We'll see some of that in a later class on verification. So the languages are quite different in terms of their syntax and how they approach describing hardware in the details. But in the high-level view of how you use them to capture a design, the process is really much the same. And much of this class is about that process of how to capture a design intent in HDL, which can be readily transferred to another language with just a few days of learning the syntax. So we've seen how to describe flip-flops in the last submodule. Let's now turn to the two ways of describing combinational logic in Verilog RTL. So let's take the same approach. We have a piece of logic on the right, a mux and two gate inputs. How would you describe this in words? Well, mux screams for an if-else statement, doesn't it? Right? So if A is selecting the top input, else if B is selecting the bottom input, describe what that is. Well, you might best do something like this. If A is 1, then foo equals B XOR C, else foo equals B or C. Well, how would you translate that to code? Well, it's already fairly obvious. I've used an if-else statement, so that will be the core of our code. In Verilog RTL, we also have to combine that with some sort of trigger statement. And so you end up with something like this. The body of this statement block is if A, foo equals B hat C, the hat is XOR, else foo equals B bar C, the bar means OR. The trigger statement is always at A or B or C. What this means is the execution of the following code is triggered when any of A or B or C change in either direction. When you think about it, that is also the behavior of any combinational logic. When does foo get reevaluated in that diagram in the top right? Whenever any of A or B or C changes. So this is so again, the behavior of the code function is implying the logic function that is being modeled. The logic is reevaluated whenever any of the inputs change, just like in combinational logic, and the behavior corresponds to that of a mux because of the if-else statement, and two logic gates because of the XOR and OR statements. And that's exactly what I'm saying here. Because we have all the logical inputs in the sensitivity list, this block is re-evaluated whenever the inputs change. The if-else describes the behavior of a mux, and we also have the behavior of the XOR or OR logic. However, unlike the case for flip-flops, where there's only one way to capture a flip-flop in Verilog, there are two ways to capture flip-flops, combinational logic in Verilog RTL. But before we do that, I did realize I skipped this, and that is that just a bit of nomenclature. An always at statement, the statement block starting with an always at statement is referred to as procedural block. The reason is quite simple. The statements in the block are generally executed in sequence, i.e. procedurally. But let's go back to the other way of coding at least some combinational logic within Verilog. This is a shorthand way to capture combinational logic that can be described in one line. It can only be used for logic that can be described in one line, and it's called continuous assignment. It's written as assign output equal some statement, some one-line statement. It's called continuous assignment because the way it is evaluated in the simulator is that the statement is re-evaluated whenever anything on the right-hand side changes. Again, this is the behavior of combinational logic in the actual logic. Foo is re-evaluated whenever any of A, B, or C changes. I'm also introducing a little bit of syntax here, the emotion I haven't seen before. That's this question mark colon statement. That means the same as if A, F. What it means is before the question mark is what we're matching against. So if A is 0, then the output is D. Else if A is 1, the output is E. So we evaluate the statement before the question mark. If that is true, we choose the first alternative. So if that is true, we choose the first alternative. Else, if that is false, we choose the second alternative. This is the same as an if-else statement. Finally, I do need to describe how you can include some combinational logic in a flip-flop procedural block. Why do I only say some? Because if your logic description is such that you have to assign to a new variable, you no longer can do this in a procedural block starting with always at pos edge clock. Why is that? What happens to every variable assigned within this procedural block? It becomes the output of a flip-flop. Thus, we can only describe within this block things that only require what we actually want to be outputs of flip-flops to be assigned on the left-hand side. Typically, you'll be limited to if-else statements or case statements. So this is an example of an if-else statement. What we've done here is added a multiplexer to the D input of the flip-flop by adding in this if-else statement within the flip-flop procedural block. Again, behavior implies function. Foo is only re-evaluated on clock edges, thus it's the output of a flip-flop. Have an if-else statement, that's a multiplexer. So quite often we add in case statements or if-else statements to bring some combinational logic in together with the description of the flip-flop, who's the output of that block. Now I must admit, some companies forbid this form and require you to clearly separate flip-flops from all combinational logic. But in this class you are permitted to do this, though sometimes it does lead to a little bit of confusion because people get a little carried away and start assigning to variables here that they did not intend to be outputs of flip-flops. So that's it. In a sense, we're done. They're the three RTL styles used to describe all synthesizable logic. Yes, we have a lot of constructs and syntax still to learn, but in terms of the core of describing synthesizable logic, they're the three styles. That's it. Always at a clock edge, flip-flops and their input logic. Always at star with, actually even always at star works, we'll come back to that later, but always at star with some signals named in that block is combinational logic. Assign is also combinational logic, though it's limited to single line structural statements. The hard part of using RTL is not the RTL syntax. We really don't need a lot of it to describe everything we want to describe, but it's design. It's working out the design intent, that's an efficient design, and then capturing that in suitable RTL. So let's finish off this unit and this submodule with some simple exercises. In this particular example, I don't have the answers given to you on the printed notes. So you actually might want to pause and draw out what you think these answers are before I present them. The first one is an always at pos edge clock with a case statement. Well, how the case statement works is cell, SEL, is successively matched to the cases on the left-hand side. on the first successful match, and only on the first successful match, the statement to the right is executed, and then we jump to the end of the case statement. So in this example, if SEL is 0, then we're selecting the adder. If SEL is 1, we're selecting B. A two-input case statement acts a lot like what? An if-else statement. So what are we describing here? A flip-flop with a multiplexer. The multiplexer is two inputs, an adder, and just B. Okay, that's the first example. The second one is some simple combinational logic. Assign H equals C bar F. Bar means OR, so what are we building here? A simple OR gate. The final one is also combinational logic, but without any edges. Always at A or B or C. Now again, a case statement, specifying 4 possible matches. On the correct match to A, the statement to the right gets executed. Well, if two version case statements were a mux, what's a 4 alternative case statement? It's also a mux, in this case a 4-to-1 mux. So A is the select line, and the inputs are B, C, 0, and 1, with the output being D. That brings us to the end of this module and this unit, this submodule and this unit. Basically describe to you the 3 basic synthesizable Verilog styles. Always at pos edge clock becomes flip-flop. Always at star becomes combinational logic, specified as behavior. And assign is combinational logic, specified as a single line in a single line via its structure. I ask you now to do the submodule quiz before proceeding to the next unit, verilog 1.2, and the first submodule within that. Thank you very much.